Welcome back to the third lecture on buck converter. In this lecture, we will discuss about the discontinuous conduction mode of buck converter. So, what happens in the discontinuous conduction mode is that the inductor current reaches a minimum value of 0 ampere at some point in the interval. In continuous conduction mode, we had seen the inductor current was like something like this. It did not reach 0, rather some minimum value, but in this continuous conduction mode, it will reach a 0 value. That is, my load current is so low that the inductor current discharges to 0 value completely, and after that there is no current flowing in this circuit for certain time. So let us assume that the inductor current reaches 0 ampere at t equal to beta times t, where beta is less than 1, because it is still not a complete time interval. It will happen within a time interval, so it is a less than 1, and this value of beta is more than the duty ratio of the switch, which is greater than 0. This you should always remember, and you can also see it here that this is D, that is the switching duty cycle of the switch, and this is my beta, which depends on the value of the components, that is L, C and R. Now we will see what happens to the output voltage, that is this voltage, during discontinuous conduction mode. Now to find the output voltage, we will apply full cycle balance to the inductor in the circuit. That is, we will apply volt-second balance to this waveform. Volt-second balance tells me that the average voltage across the inductor must be 0. So we can say Vs minus V output, that is this voltage, for the time dt, this is my dt time, this area should always be equal to this area. What is this area? We have here beta times t and here d times t, and this voltage is output voltage, that is the negative of the output voltage. We have discussed this in the previous video. So we have this area is nothing but the output voltage and the time, this interval. What is this interval? Beta t minus dt. So beta minus d into t. Why are not we taking the negative sign here? We are not taking the negative sign because we have already assumed that this area is positive and this area is negative. So according to this volt-second balance, this says that the average voltage should be 0. So the positive area plus the negative area must be 0. So we can take this negative area in this side, and we can say that the positive area should be equal to the negative area, and we do not take the sign for this negative area because we have already taken this negative in the other side of this equation, so this negative will become positive. Now if we simplify this equation, we have t cancel out from both the sides, and we have Vs into d minus V output into t equals to V output into beta minus d into V output. So we, from both sides, we see that this term is same, so it gets cancelled out. So we will get V output equals to dVs by beta, and beta is less than 1. So this is a less than 1 term in the denominator. So this is my actually the output voltage in a buck converter under discontinuous conduction mode, and we see that this voltage is more than this dVs term. Let me explain this more here. Suppose we have Vs equals to 10 volt and we have a duty cycle of the switch equal to 0.5 or 50%, then we expect output voltage to be d times Vs, that is 0.5 times 10 volt, that is 5 volt. Now if the circuit is operating under discontinuous conduction mode, and let's assume that we have beta equal to 0.8, which is more than the duty cycle, that is 0.5 but less than 1. So in this case, if the circuit is operating under discontinuous conduction mode, then the output voltage we will get is dVs upon beta. dVs we have already calculated 5 volt, that is the output voltage under continuous conduction mode, and beta is 0.8. so how much we will get? We will get 6.25 volt. So we can see that the output voltage under discontinuous conduction mode is more than the output voltage that we got under continuous conduction mode. Now question arises is how can we determine if the circuit is in CCM or DCM? So we had seen earlier that the ripple current in inductor is given by D into 1 minus D into Vs by FL, and at the boundary of CCM and DCM we have the load current equals to half of the ripple current. We have discussed this concept earlier also. So we have half of the D into 1 minus D Vs divided by FL. This is the load current, and load current is nothing but dVs by R. This is at boundary. Now from both sides D and D will cancel out, Vs and Vs will cancel out, and we bring this 2FL term to this left hand side. So we have 2FL by R equals to 1 minus T on the right hand side, and this F can be replaced by 1 over T. So we have 1 over T here, and we replace this F term. So what we have here is 12 by RT equals to 1 minus T. This is a very important equation, and this happens at the boundary. Now here this 12 by RT term, this is called the conduction parameter. Conduction parameter, and we denote it by K. So we have K equals to 12 by RT. If this 12 by RT term equals 1 minus D, that is the duty cycle of the switch, then we can conclude that the circuit is operating at the boundary. Now suppose we increase the value of L, then what will happen? Then this value of K will also increase, and this might not equal to this value on the right hand side, because we keep this D fixed, but we increase the value of the inductor. Then the conduction parameter increases, and now we can say that the circuit is operating under CCM. And in the similar way, if we decrease the value of this inductor, then this parameter will decrease, but we keep this value of D fixed on the right hand side, then the value of K will become less than 1 minus D. Then we will say that the circuit is under discontinuous conduction mode. Let me explain this in more detail in the next slide. See, we have K equals 12 by RT equals 1 minus D. Then the circuit is in the boundary of CCM and DCM, and if K is more than 1 minus D, then the circuit is under CCM, and if K is less than 1 minus D, then the circuit is under DCM. Let's see this with this plot. Here we have plotted the critical value of K, that is K crit, which is at the boundary, that is 1 minus D. When D is equal to 0, then this value will be equal to 1. This is nothing but K crit. And when D is equal to 1, then this critical value of K will be 0 here at this point. Now let's say we have the value of K, that is 12 by RT. K equals 12 by RT. It does not depend on D. So by changing this value of inductor, we can change this value of K. Let's say we have L equal to 1 microhenry in the circuit, which gives value of K, let's say 0.5. Then we have K equal to 0.5 here, and now if the circuit is operating for 0.5, here it intersects this critical curve at 0.5 D equals to, because now if my circuit is operating at a duty cycle of less than 0.5, that is in this range, then my circuit will be in DCM, because in this region my value of K is less than the critical value. How much less? this much. But if my circuit is operating, say at a duty cycle of, let me show it here, 0.8, then the value of K, that is conduction parameter, is 0.5, but the critical value of the conduction parameter, what is the critical value of conduction parameter when my duty cycle is 0.8? We can find it from here, that is 0.2. But my selected value of the inductor gives a conduction parameter of 0.5, which is more than the critical value, that is K is more than critical value. Then my circuit will operate in continuous conduction mode. So from this graph, we can say that whether the circuit operates in CCM or DCM depends on the value of inductor chosen and the duty cycle of the switch. Both of these parameters will decide the operation of the circuit. And we see that the boundary is given by K crit equals to 1 minus D, which is plotted here. And the part under this critical value is discontinuous conduction mode, and the part above it, that is this part, is continuous conduction mode. Now let us see in the next slide how we can solve problems based on this concept. Here we will learn how to solve the problems based on discontinuous conduction of buck converter. We have already seen that the inductor current waveform in a buck converter is like this, and we also know that the capacitor does not pass any DC current. So the entire inductor current, that is the DC value of the inductor current, is what is passed to the load, that is the load current, and the inductor current DC value are same. So the DC value of load current is equal to the average value of this waveform, inductor current waveform, and this is a triangle. So the average value is of this waveform is nothing but the area of this waveform divided by the time period. What is this area of this waveform? This is half into base, that base is beta times t, this value, and the height. The height is nothing but the ripple in the inductor current, that is del IL. So this t and t will get cancelled out, when we will get that the load current is equal to half into del IL into beta, and this load current is flowing to a purely resistive load, so it will produce a load voltage that is equal to the load current times the resistance, because it's a resistive load, and this load current is a DC current, so this is also a DC voltage. So we have V output equals to half into del IL into beta into R. We will use this later at this point. We also know that the output voltage is dVs by beta. So from here we can say this Vs equals to beta by d into V output. We will use this at this point. We will replace this Vs by this value. Plug it in here. We have beta by d times V output minus V output. So we can take V output common from here. So we can say beta by d minus 1 into V output, and now we can replace this V output with this value. We will replace this here. So what is V output? V output is nothing but this value that we found earlier, that is half into del IL into beta into R. So this is nothing but L di dt. This is, we are talking about the time interval 0 to t to dt. That is, during this time interval we have the voltage Vs here because the switch is closed, and we have source here, and we have output voltage V output here. So the voltage across the inductor is Vs minus V output. So Vs minus V output is the voltage across this inductor, which is L di dt. What is di? Di is the change in current, that is del IL. Here current is changing from 0 to del IL. In how much time? In the time dt. We are not considering this time for the time being. This is in dt time we have del IL current change in through the inductor. So we have L del IL by dt. Now from both sides, we see that this del IL term will get cancelled out, and also this d term, and here if we take it, simplify it like this, beta minus d into half into beta r equals to L 1 by dt, right? So this d term will also get cancelled out. So what we have is, we take this 2 on this side, we will get 2L, and we take this r from this side to right hand side, so we get r in the denominator, and t is nothing but, here we have left a beta and a beta minus d, so we have beta into beta minus d, and we know that this 2L by RT term is nothing but the conduction parameter k. So here we have derived a very important equation, that is, let me write it down here, k equal to 2L over RT equal to beta into beta minus t. We will use this equation along with the other equation, that is V output equal to d times Vs over beta, to solve problems based on discontinuous conduction mode. And what is this k called? This is the conduction parameter. For boundary of CCM and DCM, we have beta equal to 1. So just put beta equal to 1 in this equation. We will get the critical value of k equals to 1 into 1 minus d. That is nothing but 1 minus d, which we have already derived earlier. Now, if my k is more than critical value of k, then we have CCM. If it is less than critical value of k, then we will have DCM. And in case of CCM, we have V output equal to d times Vs, and in case of DCM, we have V output equal to d times Vs divided by beta. Now, in the following slide, we will see a problem based on this concept. So, let us solve this problem. Here we have a buck converter that has input DC voltage of 30 volt, switching frequency of 20 kHz, and duty cycle of the switch is 0.5. The load resistance is 50 ohm, and the value of the inductor is 500 microhenry. And they are asking what is the value of the output voltage. So if we don't check whether the circuit is in CCM or DCM, we will directly apply the formula that V output equal to d times Vs. That is, we have already, they have given VD 0.5 and Vs 30 volt, we will get 15 volt. But that will be right only if the circuit is in CCM, but we have not checked that yet. So let us check whether the circuit is in CCM or in DCM. For that, we need to find the value of the conduction parameter k, which is equal to 2L by RT equal to 2 into L. L is 500 microhenry by R is 50 ohm, and T 1 over T is F. 1 over T I can write it as F. What is F? 20 kilohertz. If we do the calculation here, we will find that the value of k is 0.4. Now, what is critical value of k? Critical value of k is, for buck converter, it is 1 minus d equal to 1 minus d is already given as 0.5. 1 minus 0.5 is 0.5. So we can see that the value of conduction parameter k, which is 0.4, is less than the value of the critical conduction parameter value, because 0.4 is less than 0.5. So this indicates that the circuit is in DCM and not in CCM, which will make our previous answer wrong. This is not correct, because the circuit is in DCM. We cannot apply this formula. In DCM, we know that the output voltage in DCM is the dVs divided by beta. dVs nothing but this 15 volt. So it is 15 volt by beta. Now, how can we find the value of beta? To find the value of beta, we will use the another equation that we found earlier. That is, what is that equation? Let me write it down again. We saw that k equal to 12 by RT, which is equal to beta into beta minus t for buck converter. So from there, here we can find the value of beta, because we already found the value of k. The value of k we found is 0.4. This is this value. This value is 0.4 equal to, we don't know beta minus, but we already know d. It is given that d is 0.5. So it is beta square minus 0.5 beta, and in this left hand side we have 0.4. So we have a quadratic equation that is beta square minus 0.5 beta minus 0.4 equal to 0. From here we can easily find the value of beta, and the value of beta turns out to be 0.5 plus minus 1.36 divided by 2. That will give you two values of beta. One of the value is a positive value and the other is negative value, but the value of beta is always greater than 0, so it cannot be negative. So we have already found the value of beta, that is 0.93. Now we will plug this value of beta in this equation to find the actual output voltage, that is 15 divided by 0.93. So we will get the value of output voltage equal to 16.12 volt. So this is how we will solve a problem based on discontinuous conduction of buck converter. In the next video, we will discuss about the boost converter and the buck boost converter in a similar way. Thank you for watching this video. If you like this video, then please subscribe and share it with your friends. If you have any doubt, you can ask me in Instagram. You can find me in Instagram by the name Tanmoy Saha. Thank you.